Now we shall look at sampling distribution of variance. We know that we calculate variance as variance of x is equal to, how we calculate variance? X minus summation x minus mu bracket square upon n, but we know that if we divide this, okay, upon n is fine because mu is known, but mu is often not known, and we use sample mean instead of population's mean, x bar, and if we do it this way, then the variance that we are going to get will not be an unbiased estimator of population's variance. What we are getting is S square, which is supposed to estimate sigma square, right? Now S square, if S square is an unbiased estimator of sigma square, then we expectation of S square is equal to sigma square. Expectation of S square has to be sigma square. Now, if we take n as a denominator, it is not the case. So we generally take n minus 1 as a denominator, so that what we get is an unbiased estimator. Let's quickly look at how it works on this particular data and try and solve it. Now, let's compute S square, which is equal to x minus x bar bracket square divided by n minus 1 is one of the S squares, and the other one is S square is equal to x minus x bar bracket square summation x minus x bracket square upon n. Okay, I've done this workout and I would simply replace the values and then we'll compute the means for each of them. So if we keep it x minus x bar bracket square upon n minus 1, the values are 0, 2, 8, 2, 0. 2820. Okay. And if we keep only n as a denominator, then 0, 1, 4, 1, 0, 0, 1, 4, 1, 0, 1, 4, 1, 0. These are the values of media. Now, if we do the sum of these values, this set of values, then the sum is, I guess, 24. Yes, the sum is 24. If we divide it by 9, that is the sample size we have, what we get is 2.66. I'm rounding it at 7. This is what we get. So, what is this? These are the sample variances. For each of the sample, we have a sample of 3 and 3. So, what I did is 3 minus 3 bracket square plus 3 minus 3 bracket square, which is 0, divided by n minus 1, which is 1. So, I keep it as it is, and which is 0. Now, here I did 3 minus 4, that is 1. 3 minus 4 is 1 square, and 5 minus 4 is 1 square. So 1 plus 1 upon n minus 1, that is 2 minus 1, that is upon 1. So 1 plus 1 upon 1 is 2. So this is how I have got these sample variances computed. Now each of the variance, after computing all these variances, we have added them. This total is 24 divided by number of samples that I have, 9, is equal to 2.667, which is exactly identical to what the population's variance is. Exactly identical to population variances. That is if I take n minus 1 as a denominator, then the sample variance is a unbiased estimator of a population variance. Sample variance is an unbiased estimator of population variance. If I don't do this, then what happens is this total is 12 divided by 9, whatever 1.33 is the answer. So what actually happens is, if I take n instead of n minus 1, my expectation of sample variances is smaller than actually what the sample population variance is. So expectation of sample variances is not equal to population variance. Here the expectation of sample variances is equal to the population variances. So the moment I change my denominator to n minus 1, the variance, the sample variance, is a unbiased estimator of the population variance, right? Is an unbiased estimator of a population variance. So we know that this factor is, if I compute expectation of expectation of the sample variance, which is not an adjusted sample variance, which is summation of x minus x bar bracket square upon n, then this is, if this has to be unbiased, then it is n minus 1 sigma square n. Okay, so this has to be factored by this, which means that if I have to get, if I have to get which means that n minus 1 upon n is the proportion with which my sigma, my expectation is away from the sigma square. So I have to multiply sigma square by n minus 1 upon n proportion, which means that if I make an adjustment here by bringing n minus 1 here, then this would be sigma square, right? This would be then sigma square, right? And so that takes care of my problem. That takes care of my problem, and that's why I do this. Now there's another tricky issue with this, and that is, just quickly look at the distributions. Okay? Just quickly look at the distributions. Okay? Now what I'm trying to do is, these are my sample means and these are my sample variances. I'm not going to look at this formula because this is not an unbiased estimator. But I'm going to show you some interesting stuff with this. Okay? Now look at the distribution. I have 9 sample means. So 3 is one of the sample mean. No, 3, 4, 5, 6 and 7. Okay. Now I say I'm simply plotting how many times I'm observing them. So how many times I've observed 3? 1. That's it. So 1, 2, 3, 4, 5, 6. Okay. 4, how many times I have observed? 1 and 2. I have observed 4 twice. 5, how many times I have? 1, 2, 3 times I have observed 5. 6, how many times I have observed? I have observed 6 twice. I have observed 7 only once. Okay. This is the distribution of sample means. Now I am plotting it discrete, but actually it should be theoretically a continuous distribution. Unfortunately, we have a sample of a size 3 and sample of a size 2 and population of size 3. So I am doing it this way. Now this is distribution of. So these are x bars. Okay, these are x bars. Okay, so this is distribution of sample mean. Now let's look at sample variance. Okay, we are taking an unbiased estimator, we are not looking at biased estimator of population variance. We are looking at unbiased estimator. What are the various values I have? Say 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. How many times I'm getting 0? 1, 2, 3 times I'm getting 0. So 1, 2, 3, 4, 5, 6. Twice I'm getting 0. Thrice I'm getting 0. 1, 2, 3. Yeah, I'm getting 0 thrice. How many times I'm getting 1? Not a single time. 2, 1, 2, 3, 4 times I'm getting 2. And 8 I'm getting twice. Right? Right? That's it. What is the difference that you are observing? What is the difference that you are observing? Obviously, you would realize that the distribution of sample mean is reasonably symmetric. But in spite of the S square, these are the values of S square, despite of this S square being an unbiased estimator of population variance, the distribution of S square is not symmetric. Point is, there is some chance that you would get a very high S square despite of most of the S square being really to the lower side. So this distribution is not normal. Probability that you will get smaller S squares is higher than probability that you will get higher S squares. Okay, what is the mean S square? Mean S square is 2.667. So here is the mean. This is the population sigma square. Okay, here is the population. Here is the population value. This is the population value. Right? Most often than not, we are getting sample S squares smaller than the population S squares, and less often we are getting them higher than the population S squares, the population sigma square, so sigma square basically. In case of mean, this is the population's mean, 5. The chance that we get a sample mean higher than the population mean is identical to the chance that we are getting a sample mean smaller than the population mean. But so is not the case with variance. Now we have made this variance an unbiased animal that has not made it normally distributed. The chance, in spite of this, the sample variance that we are going to get is more likely to be smaller than the population variance than it is likely to be larger than the population variance. And this is an idea that is important to keep in mind. Having an unbiased estimator of sample variance is not enough.